We looked at the interface of Prosper. We look at how you can input all the early requirements to do your simulation. We also looked at the PVT analysis, how you can easily use the laboratory data in order to do a PVT match. And we ended by looking at how you can develop a simple IPR using the PI model and also using the Vogel analysis. So today, we are going to start by seeing how we can develop a vertical lift performance in order to know the operating point of the system. Remember, I think, I don't have that PowerPoint here. Okay, so I already took time off to explain about nodal analysis. I talked about the inflow performance relation, and I talked about the outflow performance relation, which is also called the tubing performance relation or the vertical lift performance. And when you draw these two curves, the point at which they intersect gives us the operating point of the production system. If they don't intersect, it means that there is no way that well can produce naturally. So it shows that that well is dead. So they have to start re-energizing the system by bringing in an artificial lift, depending on where the problem is coming from. If the problem is coming from the reservoir, they can do water flooding analysis, they can do water flowing performance. They can also do steam injection, gas injection, and all of that. If the problem is coming from the wellbore, they can introduce an artificial lift method that will help to propel the hydrocarbon from the well, from the bottom of the well bore to the surface. So since we have already developed our IPR, let's plot what we did yesterday again. And you see that done. All right, so this is our IPR model. This is our IPR model that we plotted yesterday using the Vogel equation. So what we are going to do now is to plot a simple case of the vertical lift performance before we can look at other complex situations. So we'll just close this. So what we need to do now is to come to this panel and see how we can describe the well ball itself and all the instruments that are found in the well ball. So I'll double click here. You see there are about 6 items that are needed in order to describe the vertical lift performance. We have the deviation survey. Yes, we will need that deviation survey. We have the surface equipment. We may not be interested in that since we are interested in the downhole equipment. So we have the downhole equipment, we have the geothermal gradient, and then we have the average heat capacity. Remember, we mentioned at the beginning that we want to do our prediction for pressure and temperature. That's why they are asking us all these informations, because we want to do the temperature prediction also. If you just indicated that you want pressure prediction only, then you have now to include temperature survey in this area. So since we have highlighted all what we want to input, we'll go now to edit. The first one is a deviation. So what they want to know if the well is deviated. So let's just deal with a simple case of a vertical well. So at the beginning, 0, 0. Then at the end, let's just say 9,000 and 9,000 also. Remember, I have taken time to explain the difference between measured depth and true vertical depth. If you are drilling a well and that well is deviated, the measure depth is the length of the drill hole, but the vertical depth is the vertical distance down to the bottom of the well. So let me just do a little bit of illustration again. So if I have a well there, that's our deviated well. If you measure the length of this part inside, that's the measured depth. But if you take this vertical distance from the surface right down to this level, it is now called the true vertical depth. So if I have a deviated well, the measured depth should be longer than the true vertical depth. But if my well is vertical, the measured depth and the true vertical depth are the same at any given point in time. So if we are dealing with a vertical well, we'll say at the level of 0, the true vertical depth also is 0. At 9,000, it is also the same. So we can come to plot here, and then we'll be able to see that's the true vertical depth. That's the path of the well, showing that it is vertical. All right, so we'll take down there. The next one now is about the equipment. What type of equipment do we have? At the surface, we may have our X-mass tree. When we put it, we'll see what the X-mass tree is all about. We have the X-mass tree. After the X-mass tree, we have our tubing. We'll just type the tubing. Then after the tubing, we have our casing. So we'll just type the casing also. So this X-mass tree, let's just assume that it ends at the depth of let's say 30 feet. Then the tubing continues from there and ends at the depth of, let's say, 7,500 feet. And then the casing continues from there and ends at the 9,000, which is our final depth. So we want to see what is the inner diameter of the tubing. We may have 3.75. And then they're asking for the roughness. The roughness of the tubing is always provided by the company that is designing the tubing and the casing also. So the inner diameter of the casing, let's just say 7. Let's say 7. And then we take OK. The next one now is our temperature survey. We may say the surface temperature is around 65 degrees Fahrenheit. Then at 9,000, let's say the temperature is around 230 degrees Fahrenheit. Then the rate at which heat is being lost, that's our heat transfer coefficient. Let's say 8 BTU per feet per joules per Fahrenheit. All right, so we have that. Then all what we have here now is the heat capacity of oil, the heat capacity of gas, and the heat capacity of water, or the heat transfer coefficient, let me put it like that, of water, gas, and oil. So we take OK there. Then we may go to summary. You say equipment error, temperature at wellhead not specified. Done. So come to temperature. Let's go to equipment, downhole equipment. Let's put this one at 0. Our X-mass tree is at 0. Let's see if that's still. All right, so everything is okay. So you have to give the temperature at the level of where the tubing starts. So this is a brief of what we have. We may see draw downhole. We click on it. So you see everything. So this is our X-mass tree at the beginning. Then from there, we have our tubing. We are talking about the path where fluid is going to flow. We know that generally, this our casing will start from here to the surface. This our casing will start from there to the surface. But remember that there is a packer here that closes up this path, so fluid does not flow into the annulus. That was what we chose at the beginning, because we were dealing with just tubing flow, not tubing and annulus flow. If you have to talk about tubing and annulus flow, then this part now will come into play, because the fluid is flowing inside the tubing and also inside the annulus. So even though the casing goes right to the surface, but we are only interested around we are only interested in the path where fluid is going to flow, because the fluid will first of all start by flowing and having contact with the casing. Then at this depth, it now goes now into the tubing. It now goes now into the tubing. So this is our downhole equipment. Okay, this is done. And also this is done. We will go now to our calculation. A minute. Okay, so you can see clearly from here the downhole equipment. We have our X mass tree. This is our X mass tree. And then we have our tubing. This is our tubing where fluid will flow. And then from there now we have our casing. So if this is at the level of our reservoir, the fluid first of all starts by flowing in the casing before it now enters the tubing. So we'll go to our calculation. There are so many things that we want to calculate. Do you want to calculate the inflow? That's the IPR, which we have already done. You can calculate the gradient. You can calculate just the tubing performance relation. That's the VLP. But in this case, we want to calculate the IPR and VLP so that we can see where they intersect to know our operating point. So I will take this. So from here now, we need to know the pressure at the wellheads. Remember that the bottom hole pressure has to always be greater than the wellhead pressure. That's the reason why fluid is flowing from the bottom hole towards the top of the well, right to the surface. So if your wellhead pressure is greater than the bottom hole pressure, there is no way fluid will ever flow. So at this level, we will just leave it simple at 200. Our water current, we started by saying it is 0. So let's leave it at 0 first for now. Then which model do you want to use to develop your VLP? So there are different types of model. I think when I was explaining nodal analysis, Excel for oil and gas, when I did nodal analysis, I took time to explain the vertical lift performance, and I gave two correlations that are mostly widely used. We have the Pointman-Carpenter correlation, and then we have the Hagedorn-Brown correlation. So there are different correlations that you can use. Here. You have this is the Hagedorn-Brown. We have Jones and Rose method and all of that. So let's first of all, we can take Hagedorn-Brown. Then we now go to our calculation. We calculate. Okay, the calculation is done. So we can now go to plot. You click on plot, system plot, plot all cases. And then we plot this. We are plotting our liquid rate against the vertical lift pressure and then the IPR pressure also. So we take down, and then this is our system. Hold on, there's an issue with the calculation. So from this, you can see actually what the liquid rate is, what the oil rate is, what the gas rate is. There is no water rate since you said our water cut is zero. Since our water cut is zero, there is no water rate there. Let me see this again. Hold on, let me cross check this payment. We have deviation 0 to 9,000. We have the downhole equipment surface 7,500, 9,000, which is okay. And done. Go back to our calculation. Vertical lift performance curve. We have the pressure at a node. We have our water cut. We have total gas oil ratio, which is what we already input as of yesterday. Then we have our vertical lift performance from Hagedorn and Brown. We have our solution node. Okay, we are solving for the bottom node. That's okay. Well read method, automatic, is okay. Show calculating data. All right. Plot pressure, which is okay. This, let's plot this, choose by case. Okay, we have just one case here. There's an issue somewhere. Let's take the second case and see what is happening. We'll come to our vertical lift performance. If we plot our vertical lift performance, that's our vertical lift performance, which is 100% okay. Done. Deviation surface, yeah, and this we take basic. We have deviation 9,000. Yes, it's okay. Capacity is okay. Disable surface equipment, no. Okay, on the ground, disable method. We're having negative values of pressure, so there should be an issue somewhere. we're having negative values of the vertical lift pressure, which is not supposed to be the case. All right, let's take the second case and then we do the second case and see how different it is. So what I wanted to do today mostly was to introduce different types of skin effects. All right, so what I wanted to do today is to introduce different types of skin. We'll come back, we'll plot another plot and see how it goes. So if we want to introduce mechanical skin and deviation skin and perforation skin, I think we have talked more about all of this. We are going to use the Darcy's equation. Let me go to my PowerPoint and see if I have some illustration there. First thing we have to note is that we have our well that is producing from a formation. As fluid is flowing, there is some kind of activities that may take place during perforations because we have this well has been cased. This well has been cased like that. And once it has been cased, they have to produce a conduit for this fluid to flow into the well bore. So what will happen is that they have to perforate this casing. They have to perforate this casing so that fluid can easily flow. During the process of perforation, there are some kind of fluids that are also injected into the reservoir. This type of fluids can interact with reservoir fluids, and if they are not compatible, they'll produce some kind of damage around this particular region. They'll produce damage around this particular region that tends to hinder the flow of fluid or to cause an additional pressure drop. So this is how a perforation area looks like. This is our horizon, this is our well. Then this is at the depth. It has been perforated. This is the gun that has been shot to produce the perforation. If you look at it well, this one in dark is a perforation gun that has been shot. But when the perforation gun goes in, it has to damage some part of the formation around, it has to crush this part of the formation around this particular area. That's where we talk of the crush zone thickness. The crush zone thickness now is the thickness of the area that has been crushed. Then we have the perforation length, which is the length of the perforation, the length of the targeted perforation. Then this now is, we know that generally in our reservoir, we always have the invaded zone. We always have the invaded zone as a result of the drilling mud. When the drilling mud is being pumped down into the system, we remember that the pressure of the drilling mud is greater than the reservoir pressure. And once it is greater than the reservoir pressure, the reservoir fluid cannot flow into the well bore because the pressure in the well bore is greater than that pressure. So it blocks the fluid from flowing into the well bore. That is a solution because they don't want the hydrocarbon to flow into the well bore during production. But it also creates another problem because due to the fact that the pressure is higher here, the pressure tends to flow inside the reservoir, pushing the hydrocarbon away. As a result, part of the reservoir has been invaded, by the drilling fluid. So this particular zone that we see here is our damage zone or our invaded zone. This is the damage zone thickness. This is our damage zone thickness. So all of these informations are needed in order to calculate the skin due to perforation. We need the crush zone thickness, we need the perforation length, we need the damage zone, thickness. This is our casing here. This is our casing here. And then this is the diameter of the open hole. So the casing, this is the diameter of the open hole, and then that's our casing. So all of these informations are needed in order to calculate the skin due to perforation. Then another extra skin also comes in as a result of the fact that the well is deviated. If the well is deviated, there's an extra hindrance to the flow of fluid that is created. So let me see if I have some illustrations here. All right, so this is the damage due to skin effects and all of that. This is a damage due to skin effects, and this is how you calculate the skin effect due to this damage that is created as a result of incompatibility in fluids. That's not what okay. This is the skin effect due to the fact that the well is inclined. So it has a complex formula that can be used to calculate the skin due to the deviation of the well. So that at the end of the day, the total skin is, there are different skins that we have discussed. At the end of the day, the total skin in the system that caused about pressure drop has to come from what? Formation damage, have to come from partial penetration, has to come from well deviation, and then it has to come from perforation. So we have partial penetration. Partial penetration is the fact that not all the interval have been perforated. Just part of the interval have been perforated. Probably what we have down here is our water, and then what we have up here is our oil. So they have perforated only this upper part due to what? Due to the fact that they don't want the water down here to flow into the well bore. So they just want to target only the zone where oil is. But as a result of doing that, there is also an extra skin that is created because all of the fluids within this area tend to converge only towards this particular part. As a result of that, the flow stream tends to merge with each other, creating an extra pressure drop around this area, which we talk of the pressure drop due to partial penetration. So our total skin in the system is due to deviation, due to perforation, partial penetration, and then formation damage. Formation damage is due to emulsions, due to formation of scales and all of that, and so many other things. So our total skin is going to be a combination of all of these. All right, so we have talked about inclination skin, formation damage skin, partial penetration skin. Then we have described how the perforation area looks like. So we'll go back to our software. I will close this first. All right, there is always a help button here. You come to a help button, for example, you take content, it opens up. When you come to your top left up here, you see a certain search button there. You see a certain search button. I can click on search. I search on anything that I want. Anything that I want. Maybe we want to talk about maybe the Hagedorn-Brown equation. Hagedorn and Brown equation. I will search. I double click. All right, I've just put Brown there. Okay, that's the Hagedorn and Brown equation. They have talked about the vertical lift performance correlations. They have explained all the various correlations that you have there. The only disadvantage is that they don't give the formulas. The help button doesn't give the formula that is used, but all of these correlations have well-defined formulas that are used in order to develop either it is the IPR or it is the vertical lift performance. So if I come back to the software, if I want to analyze all these various types of skin, I will take Darcy as my flow equation. Once you take Darcy as your flow equation, you realize that this particular part of mechanical / geometrical skin appears. These are various ways in which various methods, correlation that can be used to characterize this mechanical skin. We have the Caracas equation. Once you click on Caracas equation, which is the most widely used, we have this Cinco equation that also appears, and other equations for deviation and partial penetration. So I will, let me see. So if I go back to my help button there, and I search on Caracas. I search on Caracas. I double click. All right, they are telling us the various things that you have to input into it and all of that. Okay, Caracas and Tara. All right. So this is describing how you can get the formation, the skin as a result of perforation. So this is exactly what I have already explained. Then from there, they have given us, describe the various parameters that the system needs in order to calculate the skin due to perforation. So this is the only disadvantage with this is that they don't give the formulas. So if I go to skin models, you see there to calculate mechanical and geometrical skin, you can use the log, the Maclade, and the Caracas-Antarix equation. And I've clearly stated here that the Caracas-Antarix equation are the most widely used in the industry to calculate the skin effect due to the mechanical damage, or what we call the mechanical skin. They have also talked about deviation and partial penetration skin, and then they've given the various equations. We have Cinco and then Manti-Bronze. The Cinco is used for deviation skin, then the Manti-Bronze is used for partial penetration. So if you're writing a project and probably you want to use these correlations, what you have to do is to probably go and check these various equations that are used. The equations are not in the software, but they have given us a reference where we can get the Cinco equation. It's an article that was written by Cinco and Miller and the rest. So you can go to this article, you'll be able to see they are talking about pseudo skin. So you'll be able to see all of these equations. So we'll go back to our software. So we say we'll take our Darcy equation. Here we'll take once this mechanical and geometric skin appears, you realize that this part now becomes red. That means you have to fill the information before the system can go on. Otherwise, no calculations will be made. So I'll take Caracas and Tariq. I'll take Caracas and Tariq. Then for deviation, I'll have to take Cinco. I'll take Cinco. So you realize that all of this also. If I want to add other things there, I may cancel this. Let me cancel this first. I will come to the first page, and then I may say we have sand control. I may put gravel park there. I may complicate it further by adding gravel park there. So I have my Darcy, my character cast, and then I take that equation. Okay, once you open it further down, you now see the sand control. We have taken the gravel part. You see that sand control also appears there. So it shows that we have to fill all of this information before we can develop the IPR. So I'll go to my reservoir model first. I'll go to my reservoir model. I think all of the data is inside the PowerPoint. I'll go to my reservoir model. I have to give the reservoir permeability, reservoir thickness, the drainage area, the delta shape, and the wellbore radius. I'm going to explain this Diaz shape. I'm going to explain that. So we have to put all of these parameters. We have 50, 100, 500. So we go to our system. We have 50, we have 100. For reservoir thickness, the area is 500.
As that is
Yes.
repeated, the reservoir permeability is repeated.
Okay, it's 50, yes. And then this factor generally for radial reservoir is 31.6, and then the radius is 0.35. Let's just leave it at 0.35. 0.35. So immediately you do that, you realize that this one becomes green. So let's go back to it. This factor is, let me just illustrate that. Generally, we have different shape of the reservoir, but we know that the Darcy's law, Darcy carried out this experiment in a cylindrical equipment. So generally, in the reservoir, they don't follow that particular shape. They are not cylindrical in direction to the experiment that Darcy's carried out. So this Diaz factor is coming is to give us how much the system deviate from the normal Darcy's experiment that we have. And all of that now is based on the shape, or is based on the shape of the reservoir. Because you may have this in this particular case, you realize that in this case, the well may not be at the center. The well may not be at the center. The well may be at a certain distance that is not actually at the center of the reservoir. So that is where this particular factor comes in. So you have to know, if you have different shapes, you have to know the various distance. So if you go back to the software, if it is not a Raja reservoir of 31.6, we can come to calculate. Once you calculate, these are the 4 things that they are asking you. They ask for the length, the width of the reservoir, they ask for the distance to the length, and they ask for the distance to the width. Is once you input all of these, it will just generally calculate this factor for you. So we'll go now to our mechanical skin. We have the reservoir permeability already that is inputted there. So what we are going to do now is we have to input this mechanical, to input all of the parameters that are needed for mechanical skin calculation. So we'll go to our PowerPoint. I think that one is there also. All right, so we have 50, 80, 0.45. So we have 50, we have 80. Okay, let me check again. 0.43, 9.2, 0.43, 9.2, 9.2. Our perforation efficiency, we will just leave it at population. I think this, we cannot be 1, because if it is 1, it shows that you have perforated the entire length of the well, but we have not perforated the entire length of the well. So let's just leave it around 0.6. Our damage zone thickness, I've already explained all of that. Our damage zone thickness is 8, damage zone permeability 25, damage zone thickness is 8, damage zone permeability is 25. Then we have crush zone permeability. Yes.
Damage zone permeability is 5. You put 8.
Damage zone, come again. Okay.
Damage zone
thickness is 8. Damage zone permeability is 25. I skipped that one. Okay, this one is crush zone thickness. Crush zone thickness is 0.2. Crush zone permeability is 12.5. So we have 0.2. We have 12.5. Then we have the short. Is 120. Then the well bore radius, we already inputted that 120. Then the vertical permeability, we know that generally there must always be a vertical permeability. But what we are just assuming is that the horizontal permeability is 1. So for vertical, because permeability changes drastically in the vertical direction. So for vertical permeability, you may put it if you have. If you don't have, you leave it. But in this case, let's just put 10 and see. Then we go now to deviation. The well is, let's say, 14 degrees deviated. Perforation is 0.6, as we put in the other case. Then we go to sand control. This is still showing red. What is missing there? Okay, short density is 8, not 80. All right. Well, you see that it automatically turns into green. So we have now sand control. What is our gravel packs? I already explained the concept of sand yesterday. Our gravel pack permeability. So we look at our gravel pack permeability. All right, gravel pack permeability is 35,000. So our gravel pack permeability is 35,000. 1, 2, 3. Then gravel pack length and gravel pack interval. Gravel pack length is 6. Gravel pack interval is 100. So we have 6. We have 100 there. Then we have the beta factor. We will just leave that. We'll just leave that one. So you see that it automatically goes to green. So once you have done all of this, you will now go now to calculate. It has been calculated. We will plot. We'll still have our IPR. That looks like what we had yesterday, but there are so many other factors. Let's see view results that have been calculated. So many things that we did not calculate yesterday, it has been calculated. We have our delta P total skin, pressure drop due to the total skin, pressure drop due to completion, pressure drop due to sand control, pressure drop due to perforation skin, and pressure drop due to, this one also is perforation. Okay, this is penetration, partial penetration. We have pressure drop due to diversion, and so on. So you see a lot of pressure drop along the line that is taking place, and they have calculated the pressure drop as a result of all of these components. So what we will do is we'll come back and replot. We will replot this. We'll take OK. I may take out the temperature. Let me see. I replot this. Let me take this temperature out. I take OK. I may want to also plot the delta, the pressure drop due to the completion. I will double click on this. That's how the pressure drop due to completion is varying as a result of rate. As the rate is increasing, the pressure drop is also increasing. We have pressure drop due to sand, pressure drop due to sand, pressure drop due to perforation, pressure drop due to damage, pressure drop due to penetration, partial penetration, pressure drop due to deviation, and all of that. So you have different pressure drops that have come into the equation, and all of this comes in to affect the inflow performance relation and change how it behaves. So let's cancel this and look at some sensitivity analysis. We are done with this. Let's look at some sensitivity analysis to see how we can vary some of those properties and see what will happen. So we have some cases. We go to cases. I will take this. What I will do now is I may take, anyway, let's take water cut. We started with 0 water cut. Let's see what will happen if it goes to 10. Let's see what happens if it goes to 50, and what happens if it goes to 70. So done. And calculate. Okay. We have our plot. Plot all cases. All right, so this is what is happening. So you see what is happening at the early stage. As the water content is increasing at the early stage, it doesn't really affect the inflow performance that much. But you realize that at the tail end, it starts affecting the inflow performance, because we have case 1. Case 1 was 0, case 2 was 10, case 3 was 50, and case 4 was 70% water cut. So it doesn't affect the inflow performance. So let's look at other sensitivity analysis also. So we take cases. Let me clear this. Let's look at the gas oil ratio. What will happen to it? We may have maybe 400, 500, 600, and then let's calculate it at that level. Done. And we calculate. Show result. Calculation is done. Then we plot all cases. All right, so you see what is happening with the gas oil ratio. The first one, this is our case 1. This is our case 1. This is our case 2. The one in the middle is our case 2. And then the last one is our case 3. So you realize that as the gas oil ratio is increasing, it is affecting the IPR greatly. The IPR is also dropping as the gas oil ratio is increasing. So it is affecting the IPR a lot. So you can decide to do sensitivity analysis for so many properties. There are various things that we have inputted there. You can do sensitivity analysis for anyone you want. You can go to gravel pack permeability. Gravel pack permeability, remember we put it at 35,000. We may have 30,000. We may have 35,000. 1, 2, 3. We may have 40,000. 1, 2, 3. And then we may also have, let's say 70,000. Why not? 1, 2, 3. So we take done. And then we calculate. And then we plot all cases. And then, wow, you see how it is now affecting our IPR. You see how the gravel pack permeability is affecting our IPR. So what it does is it increases. As you're increasing the permeability of the gravel pack, you are gradually increasing the performance of the reservoir. You are increasing the performance of the reservoir. Remember that the gravel pack is placed at the sand face, at the point where fluid is leaving the reservoir into the well bore. So that's where the gravel pack is placed. So it is now acting as part of the reservoir. It's not acting as an extension of the reservoir. So if you are increasing its permeability, you are also indirectly increasing the ease at which fluid will easily flow into the well bore. So as you're increasing the gravel pack permeability, that is how the inflow performance is also increasing, giving it a better performance, giving the reservoir a better performance. So there are so many things that you can do sensitivity analysis and try to see. You might also want to change the angle of the well, the angle of inclination of the well, to see how it's going to affect the skin, the skin due to deviation and all of that. So there are so many things that you can do at the level of IPR. So we have developed a simple IPR using our Vogel equation. Now we have now developed a complex IPR that has a mechanical skin, that has a deviation skin, geometric skin, partial penetration skin, and also has the effect of sand control. We are not saying that all of these things must happen at the same time. You may have one and the other one does not exist. You may have one and the other one does not exist. So at the end of doing this, you have to do sensitivity. You have to do sensitivity analysis. All right, so what we'll do now is we'll go back again and see what the problem is at this level. All right, so we have developed our inflow performance relation. We come back here. Let me just redo it and see if it's the same before I start checking where the problem is coming from. Okay, it shows that there was actually a problem with our IPR. Maybe in saving it, something changed there. There was a problem with the IPR. That's why we had that issue in the first case. So this is what we are going to have as our nodal analysis. So it gives us our inflow performance relation, and it gives us our vertical lift performance. This vertical lift performance can change slightly depending on the model that you have used. Remember, all those things that we plotted is here. So we can also plot maybe the liquid rate. Okay, this is the point of the liquid rate. That's where the point where the two intersect. That's where we have our liquid rate. We have our vertical lift pressure that have been plotted. We have our pressure drop due to total skin. We may plot that to see how the pressure drop is varying as a result of the total skin. So we didn't have that equation in the first case because probably there was an issue with our IPR. So you can always click here to remove or put in a particular curve. I can take this off. You see that one will go, I take it and it comes back. So this is what we call nodal analysis. This is nodal analysis, analyzing the system to know the performance of that system. And if I take this off, you can see the total results here. You can see the liquid rate, that's the liquid rate. You can see the oil rate, that is the water rate. The water rate is 0 because we have a water cut of 0. So if I change this to, let's say, 10% of water, because generally you must always have water, I recalculate, you realize that it has now changed. Water is now flowing at the rate of 149 point something stock tank barrel per day, while oil is flowing at the rate of 1,400 and something stock tank barrel per day. So as you're changing all of these parameters, everything also has to change. You can also do some sensitivity analysis. Oh, there's no sensitivity plot here. You can do some sensitivity analysis. Let me see, sensitivity. Okay, option. No, that's not really. This one should be having sensitivity analysis. I don't know why it's not showing. All right, we can come to cases. You come to cases. All right, you change whatever you want to change. Let's see our water cut to see how it's going to affect our system. We have 10, we have 50, and then let's see, we have 70. We have 70, then we take done, and then we calculate, and then we show the result. And then we can now plot sensitivity plot. Let me see. Plot system, all cases. All right. All right, so that's what is happening. So you're seeing what is happening with the IPR as water cut is increasing. Now you see what is happening with the vertical lift performance. So that's what I explained already. You realize that between this inflow performance and these two cases, they are not intersecting. That means if the well is existing at these two conditions, if the well is existing at these two conditions, there will be no flow. That well will be a dead well because no fluid will flow to the surface. Why? Because there is no interaction between the IPR and the vertical lift performance. So if you look at the nodal analysis, your essence is to identify where the problem is coming from. The well is not flowing. Is it that the reservoir is not performing, or the well bore itself is not performing? If the reservoir is not performing, we could definitely bring something like water flooding to see how to push the oil. Maybe the oil, the reservoir pressure must have died down and there is no sufficient pressure enough to push the hydrocarbon. So they may bring in water flooding or steam injection or gas injection. If it is the well bore that is not performing, they may now realize that the reason why it's not performing is because of high water cut. What they have to do now is to look at the production data and try to see how they can analyze it to know the source of the water cut, to know the source of that particular water cut. Where is the water coming from? So you have to analyze it to get all of that. It may be from aquifer, it may be from the water coning, which I explained yesterday. It may be from water coning, it may be from flow behind casing, it may be from channeling. So there are different causes of water. So the job of the engineer is that in that particular case is to identify where that water is coming from and see how to solve that particular issue. At this particular point, the well is considered as dead well. The well is considered as dead well. Okay, so we may also just try to complicate this vertical lift performance a little bit by looking at this deviation data. Instead of making it to be just vertical, we can make it to deviate a little bit. So I'll go to Excel. I think I had a deviation data there. I opened the wrong Excel. Okay. All right, yes, these are deviation data. For measure depth, I will copy this. I'll copy this for measure depth and I'll put it here. paste, and then for our true vertical depth, I'll copy it, copy, and then I paste it there. So that's our deviation. So you realize that you can see the displacement. When I go to plot, you realize that the well is not a vertical well. It is not a vertical well. So I will take that as okay. I will also go to downhole equipment. Well, it may be okay. Let's see. I think I have another data here. We could also use that. All right, downhole equipment, we could use that. We have the X-Mass tree, we have the tubing, we have surface safety valve, then we have the tubing and the casing. Well, no problem. Let's just leave it like that. We don't need to complicate it. Let's leave it like that. So I take okay. I go to my geothermal gradient. We have to verify everything. All right, that's my geothermal gradient. It ends. I think geothermal gradient is considering the true vertical depth. I think when I was doing I think it was week 3, the application of drilling and stuff like that. I explained the usefulness of the measured depth and the true vertical depth. I think in the situation of calculating geothermal gradient, we are using the true vertical depth. Let me see if the calculation will go. So we go back to our calculation. We go to system, then we calculate. All right, the calculation has been run in that particular case. So let me take cancel and see. So if you come here for this geothermal gradient, instead of using 9,000, for example, you go and you use, let's go to deviation data. You go and use 9,275. They'll tell you that the system does not recognize that because the depth is already greater than what we have. Our vertical depth is ending at 9,000. So you cannot be going beyond 9,000 because when we are calculating our geothermal gradient, they are looking at the true vertical depth. So all of this is okay. So we have done for simple cases. We have seen complicated cases. So the summary, you see everything that is included there. That's a summary of everything. Then I close this done. I go back to my calculation. Then I go to my system. All right, we have already calculated this, so you can plot now. And then you plot all cases. Then plot that. Remember, let's remove this, our sensitivity analysis. So for cases, I will just play data. Then I'll take run. Cases, I'll play data. All right, nothing there. Right, done. So I'll run my calculation. Let's run it for normal situation, not a sensitivity case. We plot all cases. Okay. So this is our vertical lift performance and the IPR for the deviated well. So you can make it simple, you can make it complicated. Remember that our flow rate has drastically changed. It was at 1,400 and something. So you might just look at the plot and feel that nothing actually has changed on the plot, but all of these parameters here have changed. The liquid rate has changed, the oil rate, the water rate, the gas rate, all of it has changed. So you don't just feel that because the plot is looking similar, nothing has changed. There's a whole lot of change that must have taken place there. So you can always plot your simple case and your complex case. So what we have done is to develop our IPR and the vertical lift performance for simple case and for complex cases that have deviations, that have mechanical skin and all of that. So I think this is what we planned for today. Unless you have a question, we'll call it a day.